next speaker, and he will tell us about small noise limits or diffusions.
So I would like to thank the organizers for the opportunity. This is joint work with my colleague Suresh Kumar from IIT Bombay, who is from Thiruvananthapuram, and he was here last week, I think, to talk about viscosity solutions. Okay, so the idea is, the broad idea is the following. So we look at this Feynman-Cart semigroup. So X is some diffusion process. So the Feynman-Cart semigroup is the capital T sub T of S is defined by the conditional expectation starting from X. I'm hoping that everybody has the background in diffusions and Brownian motion, etc. If not, I can add some more details. So if this e raised to 0 to t kxs ds term was not there, it would be the usual transition semigroup of the Markov process X. But with this term, it's called the Feynman-Cart semigroup, and historical origins are in the in Katz's idea to basically complexify time in the Schrodinger equation to convert it into heat equation, and then this k is corresponds to the potential term. So and what he achieved was to convert the Feynman integral into an integral on the Wiener space. So in the original Feynman-Cart's X is a Brownian motion, but now with Ito calculus, etc., one can do these operations much more generally, and so I shall be looking at a diffusion process X and the corresponding semigroup defined as above. And what my interest is in what's called normalized Feynman-Carts, which is this S sub t. And this is not a, so you just simply normalize. So this will be effectively the integral of f with respect to some probability measure, and this defines the probability measure. So the problem we want to consider is to look at a diffusion which is driven by a small noise. That is, the Brownian motion is weighted by a very small epsilon, say. So that you consider the parameterized family X epsilon. And we'll consider two different formulations. The first is less interesting than the second, but I think it helps put things in perspective. And then look at the large time and small noise asymptotics. Namely, you first let t tend to infinity for fixed epsilon and see what it gives you, and then let epsilon go to 0. So this is the Feynman-Cart's analog of small noise limits for stationary distributions of Markov processes. So again, if I didn't have the potential term there, it would amount to looking at small noise limits of stationary expectations, which have been studied by Friedlin and Wenzel extensively, and more recently, one of my students, Anup Bishwas, and I have some work extending some of those results. So this has the same flavor, but we don't go as far. I mean, the aim, at least for the present work, the aim is rather limited, as I will describe later. And I also want to mention that this has been extensively studied. The discrete time version, in particular, has been extensively studied by Del Moral. And this comes up in particle filters and things like that, and several algorithmic kind of models. But that's also my original motivation. Anyway, let me have a slide on that. So the idea was to think of K as some kind of a reinforcement mechanism. So if K is positive, you add more weight, and if K is negative, you decrease. So you kind of reinforce the particles or the number of density of particles which are giving high payoff, and de-emphasize those giving low payoffs. And what one wants to see is whether it concentrates, where it concentrates rather, if you consider both the large time and small noise limit. And so I have a few bullets here. The first one that ignore the parenthesis, that's somewhat misleading. But the motivation was there are a lot of what one might call population algorithms. So even you can think of things like genetic algorithms and so particle swarms. There are lots of things. They have certain one commonality, namely that you have several individual particles doing their own optimization, and there's some interaction which reinforces or discourages the right kind of behavior depending on the given payoff functions. And you hope that asymptotically things will concentrate on the optimum. The whole population will concentrate on the optimum. So there's an analysis in this spirit of genetic algorithms by Raphael Cerf long back. So what one does is look at t tend to infinity, look at the stationary behavior, let the noise go to 0 and see if it concentrates on the optimum you are seeking. So that was our original motivation. So the reason that parenthesis is not quite right, I just wanted to draw analogy with Liouville equation which describes kind of evolution of density of particles. But what we are, as you will see later, if you consider the stochastic representation of Feynman cards, we are actually looking at the backward equation in probabilistic terms, not forward. And although time will move forward, but essentially the interpretation is that this, I mean, it's the backward equation with time flipped, essentially. Okay, and as I said, so there are two aspects to it. One is that each particle has its own dynamics, and there's a reinforcement mechanism, and they interact. And the issue is which dominates. So as I said, I'm going to consider two separate cases. The first one is less interesting, and that's the one where the dynamics dominates, and you don't get anything very interesting. The second one is the one which gives some interesting results. And the important difference is that how you scale things, how you put the powers of epsilons and where you put them matters. That makes the difference. Okay, again to give some sort of perspective. So the idea of considering ill-posed problems as kind of small noise limits was apparently proposed by Kolmogorov. I don't know the exact reference. I've seen it referred to in this famous survey on chaos and strange attractors by Ekman and Rowell. They don't give any reference, but they attribute to Kolmogorov the idea that if you don't have some kind of a ill-posed situation and you add noise to make it well-posed and then let noise go to 0, hopefully you get a unique limit, and that's the natural limit you look for. And this has been used in several places. In game theory, there's a well-known paper by Foster and Young which proposes this kind of mechanism for selection of Nash equilibria, which are typically too many. And so they describe situations where you add noise and let noise go to 0 and characterize something called stochastically stable equilibria. More recently, this has been also used in an interesting paper by Jackson and I forget the author, Matthew Jackson and colleague on this social models of social network formation. They also look for stochastically stable equilibria in a game theoretic kind of paper. Then Shankar Shastri had studied nonlinear circuits where he sort of captured things like this hysteresis kind of phenomena as small noise limit of some dynamics. And this, anyway, you are familiar with viscosity solutions. If you look at viscosity solutions for the ordinary differential, the AJB equation corresponding to control of ordinary differential equations or degenerate stochastic differential equations, one can think of that as adding noise, which adds basically, if you add a epsilon times Brownian motion in the PDE, you will get half epsilon square Laplacian term, and then you let epsilon go to 0, and that's one way of thinking of viscosity solutions. So anyway, I motivated this by saying that small noise limits provide a selection principle, but that's not what we are going to do. We are considering very tame problem where the limit is unique. We just want to see what kind of scaling leads to what limit. We hope to pursue this further and look at the more interesting cases and also hopefully look at the associated large deviations and so on. So let me start with the first model. So here, so this is the noise perturb diffusion. So there are two perturbations. One is this, the drift M is perturbed by this epsilon times B, another small drift, and the noise is square root epsilon times the Wiener process. And I make these assumptions. These are again, the assumptions are also rather strong, but we will stick to them. This kind of things are not uncommon in control of ODEs. But again, that's because they kind of force a unique attractor and so on. So make things simpler, but it would be good if one can relax these. So there are similar conditions on M and B, except that on B it's rather lax. I mean, I can allow, for example, B identically 0, but on M it's somewhat stringent. And payoff function K, I assume is something like sort of decreasing to minus infinity. So this is to ensure that some kind of stability. I mean, you don't want things to, if you are trying to maximize the payoff and the payoff is ideal at infinity, your process will drift towards infinity. So consider some nice payoff function which has a maximum and then decreases towards minus infinity at infinity. Okay, so this that's why I also assumed that it has M as a unique 0, and that one can show that that will be a unique globally asymptotically stable equilibrium. And what's more, you get this that condition, as I mentioned, is strong, and what it achieves is that particular inequality. Namely, that if you start two processes with the same dynamics with different initial conditions, they approach each other exponentially. So this is the special case of notion called asymptotic flatness, which was introduced by Basak and Bhattacharya for in ergodic theory of diffusion process. That's a little messy to write, but essentially that would also work, because this is all we need, this conclusion. Okay, so the Feynman-Kautz formula is this. So what is actually usually one thinks of it the other way. So given this parabolic equation, its solution, unique solution in that class has this stochastic representation where the x epsilon is the process given by the diffusion which I described earlier. So I consider the normalized Feynman-Kautz formula. So plugging in f identical equal to 1. Now this can be characterized by this coupled differential PDEs. Now the second one is a self-contained semilinear equation. Given the solution of the second, the coupling is one way. Given the solution of the second, the first becomes a linear PDE. Okay. So now let me consider a related equation. So let phi epsilon beta epsilon be a unique solution to this quasi-linear elliptic equation. So this arises in, see, the way we arrived at this is something people in stochastic control are familiar with. This is the AJB equation for average reward problem for this particular control. So if you were to maximize the long-term average reward, if you want to maximize the long-term average, so this is your reward and this is the penalty you pay for the control, minus sign there, and this is the dynamics. Then the Hamilton-Jacobi-Bellman equation will be this. So the equation in two objects, phi and c. I should have written c here. And the equation uniquely specifies c as the optimal cost. So that part that is unique, and this gets uniquely specified. Yeah. The equation itself specifies it uniquely only up to an additive scalar, because if I add constant to phi, it doesn't change anything. But I have sort of forced uniqueness by imposing this condition. That's arbitrary. I could put phi extra equal to anything and there will be a unique solution corresponding to that. So in this class one can show that this is a unique solution. And what asymptotic flatness ensures is that this remains bounded. So this is the part we need. I should have mentioned another thing. That so one other way you come up with this particular control problem and this particular equation, that is when you look at the risk sensitive control problem, when you are trying to minimize or maximize the asymptotic growth rate of exponential of integral cost. So suppose you have, so let me consider minimization problem, which is what one usually looks at. So this is the risk sensitive control problem. You are trying to minimize the asymptotic growth rate of something. This is quite popular with finance people. And you get the AJB equation ends up being a nonlinear eigenvalue problem, and you do a Koloff type logarithmic transformation, you get this. And this is easier to And the standard way of analyzing the HJB equation of that is to do the log transformation, look at this and analyze this equation. And you often have similar kind of similar methodology is also used extensively in large deviations. Okay, so let's consider this particular control problem. So you want, so this is my new, I have added the control to my original equation and impose this as the reward which I want to maximize, and this is the associated Hamilton-Jacobi-Bellman equation. And now consider this process. So here basically this is the specific choice of u. Okay, it turns out to be the optimal control for that problem. And then this can be given this object, the capital phi f sub epsilon, which I was looking at, has this expression. One can show that y epsilon has a unique stationary distribution mu epsilon, and therefore I'm missing a limit t tending to infinity on the right hand side. So this limit is same as the limit. No, this is okay. Sorry, t is only on the left. Yeah, so this is correct. So this is equal to that. So it's a very brief sketch of the main idea. So the first part is actually easy. So this is what you are looking at. This is the kind of object. So you go back to the HJB equation. Here k minus beta appears. So suppose I take k minus beta here, put everything else on the right hand side, and plug that in. You will get. So you apply Ito formula to this phi epsilon of x epsilon t, and you will get the entire Ito terms, which and where you get this the infinitesimal generator operating on phi. So you get rid of that by using that the equation and this, and you get equality. This is same as all this. Okay. So then what you do is notice that this actually is a Gersonov type exponent. So you just change measures and you have what you want. Similarly, the denominator gets transformed similarly. Now you need to do some work to show that the y epsilon is actually a stable diffusion and has a unique invariant measure, etc. But again, that HJB equation facilitates a Lyapunov type stability condition because of my assumptions on k.
What is mu epsilon? Mu.
Mu epsilon is the stationary distribution of y epsilon. So that's the So as I said, I should have put some constant c here. So this becomes an equation in phi and c, and optimal. So this is a unique solution, and you can characterize beta epsilon as the unique constant appearing here is also the optimal cost. So the main result is that this mu epsilon concentrates on the asymptotic equilibrium for the ODE x dot equal to mx, and you get this result. One can also show that this actually converges uniformly on compact. So this is similar to the kind of things one gets in. So this is like when you do this Friedlin-Menzel kind of analysis, you get this kind of integral there as well. This, as I said, is not terribly interesting because what it says is that we will go to the next. It didn't depend on B, which is not surprising because B anyway is getting dominated by M. But it didn't depend on K either. The reinforcement made no difference. The dynamics dominates completely. And as I said, this asymptotic flatness is needed for handling the quasi-linear field. So this is a limitation of our technical limitation. We did what we can, and we are not PDE experts. So I'm sure somebody can do better. So I'll tell you exactly where it is needed. It's needed for this boundedness of gradient. Okay. So the usual way one approaches this is by considering the discounted cost problem and then taking this kind of discount factor vanishing to 0, and this gives you the the asymptotic flatness gives you Lifschitz condition for the discounted value function and so on, and all these things to pass through assorted limits and finally end up with this. Okay, so let me come to the second model where the conclusions are, I feel, are more interesting. So here, got rid of m. So put m equal to 0. The scaling is also a little different, and let me describe it a little bit. So I have square root epsilon here and here. So the thing is that the way one usually scale, if one was doing pure time scaling, so suppose I have dxt is bxt dt plus dwt, and I just wanted to scale it by square root epsilon, I would put square root epsilon here and epsilon to the 1/4 here. Okay. So here the noise is being killed faster than the drift. So it is the whole thing of course is being treated as a perturbation, but this is a kind of a smaller order perturbation than this. Now I put a stronger condition on B, and K essentially the same condition. Need this additional condition for technical reasons. So I need some kind of a Lyapunov type condition, assuming the for grad K here. Okay. So let's consider this normalized Feynman cards. So again, by similar arguments, you get this JB equation for certain average cost control problem, and you can write the object you want in terms of as the ratio of these two expectations, where y epsilon t is given this way. What's more, y epsilon has a unique stationary distribution mu epsilon, and this is also uniquely characterized via this pair of partial differential equations, and we have this limit. Now when you let epsilon go to 0, you get f concentrating on x star, where x star is the point at which k attains its maximum. So now it does give you the desired behavior. Again, this phi epsilon one can show as a limit and so on. The pay of k is maximized. Now again, B does not affect the limit, but we cannot get rid of that because we did use the stability of the diffusion process all the way. If it was pure Brownian motion, the result may be true, but we don't know how to do it because all our arguments are via stationary distributions and so on. We need the stability. That's more or less it, but the main thing, more interesting thing would be to look at multiple equilibria and whether this gives a selection principle on where if K has multiple maxima, say local maxima, can it does it pick the right one, or what can one say about it in general? So that will become messy, and those of you who are familiar with Friedlin-Wenzel theory know that it's, you have to look at kind of Markov chain, asymptotically the process behaves like a Markov chain between assuming finitely many equilibria, among equilibria with a rare transition from one to the other and so on. It's a very complicated analysis. The other thing one would like to relax is the strong condition of asymptotic flatness that was kind of imposed because we don't know how to handle that particular PDE otherwise. That's basically it.
Any questions, comments?
Yeah, I have one. Just now we talked about the diffusion directions exploiting, for example, the diffusion algorithm for Markov's right? Do you know any simple case using these Feynman formulas to say something about the rate of convergence of the diffusion to the Markov chain, the stable behavior of the diffusion?
Rate of convergence for Markov chains or the Feynman cards?
Via these Feynman formulas.
Can't think of anything. So you mean the
What do you mean by the study when it's having convergence of zero diffusion converges to a manifold chain.
Yeah, okay, so maybe I'll. So what Fradlin and Wenzel do is the following. So suppose you have. So if you have some diffusion like this, what they show is that mu epsilon is sort of like e to the minus some potential by epsilon square rather. Okay, so in the sense that epsilon square log of mu epsilon blah blah will go to minimum of this or that, and if W has multiple minima, so if you look at the stationary distribution, start with the stationary distribution initial condition. It's a stationary process. You look at the stationary law. If in the epsilon tending to 0 limit, it looks like behaves like a Markov chain with these states and sort of rare transitions. So these are proportional to the e raised to 1 by epsilon square times the action function, and they use this to basically characterize what will happen as epsilon tending to 0 limit. So there's an explicit formula for stationary distributions of finite Markov chains called the tree theorem. So what they show is that, of course, once you write it like this, you can guess it. They show that it will concentrate on the minima of the global minima of the potential function. So this is what the Foster and Young used in their definition of stochastically stable Nash equilibria.
So it didn't use the final fact form.
No. No, this looks at the stationary. It doesn't look at the convergence to stationarity. You start with the stationary situation and look at the small Nash limit.
Any other? Yeah.
You were not satisfied with your results, right?
Yeah.
What would satisfy you?
No, one thing is that, okay, so this is certainly one thing we should.
No, forget about the hypothesis. What is the result you are? What will be the ideal result which you expect?
There are these two directions. One is, of course, some selection principle in case of multiple equilibria. So you should come up with something like this W of Fradlin and Wenzel and be able to say that it will concentrate on the limiting stationary that mu epsilon as epsilon tends to 0 will converge to the minima of that function. That's what one expects. But the other thing is technical. That see this is inherited from the work on risk sensitive control. That equation is generally studied under some strong conditions. This is one of them, which was actually introduced by Fleming and McInerney. This is asymptotic flatness kind of condition, but I don't think it has been analyzed in sufficient generality yet. There are a lot of people who have worked on this sensitive control, including Benson, Nagai, and others. So each work handles some specific situation.
So your first case is that there is no multiple equilibrium, there is unique equilibrium.
Yeah, that's what we have assumed. Yeah. I think this kind of result would be are interesting for multiple equilibria because the purpose is to come up with a selection principle.
If there are no further questions, let's thank the speaker.
So first of all, I would like to thank the organizers for giving me this opportunity to present my work. I supposed to not come in this session. I asked Utpal why you put me this session with process because yesterday he was just telling to Professor Sundar that this is for distinguished speakers or something like that. So then I told him that I am not a distinguished speaker. So then anyway, thank you Utpal and Sheetal for giving me this opportunity to share my work on martingale solutions for stochastic Navier-Stokes equations with Levy noise.
This is a joint work with Professor Sridharan. Well, is that okay? Yeah. So then, I think you would have heard a couple of talks on this Navier-Stokes equations with Levy-Nice after the introduction of Levy-Nice by Professor Barbara. So I'm going to just give the initial. This is the plan of the talk. Initially, we give the formulation of the Navier-Stokes equations with Levy-Nice. Then we will talk about the martingale problem. So martingale problem for the Navier-Stokes equations with Levy-Nice. And then how we will see how it deviates from the usual strong solutions or the weak solutions for the stochastic differential equations. Then we derive the appropriate moment estimates and show the tightness of measures. This is also, I am just talking, whenever I say I am just talking about the students who are sitting over here, not the professors or the stochastic experts. So then Professor Sundar was talking about this tightness of probability measures. It's all the convergence of measures. This completely talks about the convergence of measures. Then we are going to mainly use those convergence of measures to get these martingale solutions for this Navier-Stokes equation. So then then we will discuss about what are the main issues either in 2D case or 3D case. Then finally we go for the uniqueness of martingale solutions. So this is the model, Navier-Stokes equations. If you just have this part, then Professor Sridharan derived this equation. Then this is the equation with the Gaussian Nice, then with the Levy-Nice. So the Levy-Nice, we are going with the two parts, one with the jump size less than 1, then the other with the jump size is greater than or equal to 1. It will be very clear when we go for the Levy-Kinchin formulation. This is the actual formulation. This is the process with the finite variation. Then the process, the Levy-Kinchin formulation says that if X is a Catalog process or the Levy process, then X equal to can be decomposed into 3 parts. One with the BT, maybe I can write it somewhere. Then that L of t, the process can be written as something like BT plus LT. L is with some size less than 1 plus which is greater than 1. So then it looks like that formulation what we have it in the Levy-Kinchin formulation. This is the term which corresponds to the jump size which is less than 1. This is the term which corresponds to the jump size of greater than 1. This is the integral, compensated integral. We will see quickly what you mean by a compensated integral, and this is the just a Poisson integral. Then with the incompressibility condition delta t equal to 0 on the boundary, in the domain O cross 0 comma t, and we post the Dirichlet boundary data and also with the initial condition. Then here the domain O is a bounded domain. First we talk about the bounded domain case when n equal to 2 or 3. Then we go for the unbounded case. When we go for the unbounded domain, then we have to talk about the far field velocity of this fluid velocity u that goes to 0 when x goes to infinity. In when the case of O is unbounded. Then u is the velocity field and v is the pressure field. Then g is the random external force, and nu is the kinematic viscosity, and w, this is the Hilbert space valid Wiener process which is independent of the Poisson measure Pk. And then motivation for these stochastic forces, most of the engineering scenario one may see that this aerodynamic flow is subjected to some forces due to some sexual vibrations or the magnetic fields and or some other environmental disturbances. So then this is the functional setting we are going to use throughout here. H is the usual divergence free space, then V is the space defined by V in H1, H01 norm, just that this is divergence free. Then P, this formulation is you have already seen that this PH is the Helmholtz projection and A is the Stokes operator, and then the nonlinear operator B. With this simple introduction, we quickly go for the semi-martingale formulation of the stochastic Navier-Stokes equations with the Levy-Nice. If you apply the projection operator and the whole set of equations, then we ended up in the equations. This omega delta will come later quickly. This is a path space we are going to work with. Then this u of t, u naught is the initial data, plus this is the finite variation part, this part which corresponds to the finite variation, then plus the martingale part. Therefore, any process with finite variation and the martingale part, this is a martingale. Any process, if you have an x of t, that's equal to something like a of t, some other part, this is m of t. This is the process with finite variation. Then this is martingale part. Then such a process usually called the semi-martingale. X of t is the semi-martingale. This is a more general formulation. You can see that why this is a semi-martingale. We have started with that in the large jump case. We have started with that just Poisson tandem measure. Then we have just compensated with this Levy measure mu. Then we ended up in this MT. MT is the martingale. This is a martingale term. This is a martingale term which corresponds to small noise in the small jump, and then this is the martingale which corresponds to the large jump. So then, with this introduction, we can go for the assumptions on the noise coefficient. Then Q is a positive symmetric trace class operator on Ketch. Then this stochastic process WT is to be a Ketch valued FT adapter process with covariance operator Q. Whenever this condition is a standard one-dimensional Wiener process, and this is a FT martingale. Then in fact, you can quickly see that I am just comparing that whatever Professor Sundar was talking about, so that we can, the students can quickly understand what's happening here. He was talking about WT is, I think, Wiener process. Then he expressed W of t in terms of just, he expressed like W of t in the basis function sum over k, ek. This bk is the one-dimensional Brownian motions, then into the ek is the basis function in Ketch. Then he told that the expectation he proved that in fact this expectation of this guy W of t is infinite, right? You proved that this is equal to infinity. Then in this case you can see that this is finite, because we have that this Ketch is W is a H-valued process with covariance operator Q. Then this is a process which again stays in the Hilbert space Ketch, because the trace of that operator Q helps to get the finiteness in this process. Here beta k is the one-dimensional, again the Brownian motions, this ek are the orthonormal basis functions in Ketch. So then LHS, we introduce the space of all boundary linear operators LHS from H to H such that this is finite. Then the trace norm SQ S star is nothing but we are defining the trace norm of this operator. Then this Gaussian noise coefficient sigma satisfies this continuity condition and also the linear growth condition. So then we introduce the jump measure. Z is a separable Banach space and LT is the G-valued Levy process. Then the process with the right continuous and left limits, that's delta L is nothing but L of t minus L of t minus, that is the right continuous with the left limits for t greater than or equal to 0. Then this is a Poisson tandem measure. This is a number of jumps occurring in the interval 0 to t, including the time t 0 to t, such that this the jump size delta L of s, this goes to the set gamma, where gamma is a Borel sets in G minus 0. We are not including that the jump size of 0 size, because that may be infinitely many. So this is a Poisson tandem measure or the jump measure associated to the Levy process L of t. Then we quickly come to the what is the compensated Poisson tandem measure. This is the compensated Poisson measure. This is the Poisson tandem measure we just introduced. Then this is the compensator of the Poisson measure that makes that integral as a martingale. We have a small jump and large jump. Then this compensator completely makes that integral as a martingale. Here this then the Levy measure or the intensity measure is given by the average number of jumps occurring in the unit time, that's given by mu k. So the compensator of the Levy process L of t, that's again this is the compensator, then again this Lebesgue measure dt. So now then this integral is the compound Poisson process. Now it's clear that why this is a compound Poisson process and this is a compensator Poisson integral, because we have compensated with this intensity measure. Then the intensity measure mu k and z satisfies, we are assuming that the jumps of size 0 is always 0, the measure is always 0, then this measure mu k satisfies this minimum, this notation tells us the minimum of 1 on g square is always finite with respect to this Levy measure is always finite, and also we need this condition to go for the higher order moments of this Levy process, otherwise we don't need this condition. So then with that assumptions on the Levy measure, we can pose the assumptions on these coefficients in the jump noise. this satisfies this continuity. Again, this satisfies because we have assumed certain conditions on this measure. Then we can guarantee that whenever it is, for instance, this measure, this pk satisfies something like we have the pk of u comma zk minus pk of v comma zk. This guy is let's say bounded by something like your u minus v into zk. Then the measure condition we have just posted on the left side tells us that this square is always finite. Then integrate with respect to the measure mu k of dz dzk. Then integrate with respect to the measure mu k of dzk, whatever be the, whether this is jump size of greater than or equal to 1 or this is less than 1, less than or equal to 1 mu zk. Then we have already posted that this Levy measure mu satisfies the finiteness conditions. Therefore, we can expect that that integral is finite. Therefore, these two conditions or one can get it. So now we are coming to the formulation of the martingale problem. Path space we are going to work with. This is a square space, and this is the usual space coming from the energy estimate. This is going to be the path space for us. D is the class of catalog functions going from 0 to 0 comma t to into v dash. Then the catalog functions are the right continuous and have a left limit at any point t in 0 to t. This f tilde is the sigma algebra Borel sets in omega tilde. Then we are going for the canonical filtration generated by those size, that is ft tilde. Then the measure, induced measure p is a measure on this space, probability space omega tilde f tilde ft tilde. So suppose if u as the generator, the transition semigroup T of t, then we can define the generator, but we don't know whether it has a semigroup T of t. Then if it has, then we can define LF is nothing but it's not that the TTF in other way around. We can define the conditional expectation of f given that the process starts at x. This is what we have been seeing so far. This is the generator. Then for every f in the domain of L, where domain of L is the all functions going from h to r such that this limit is exist. So whenever f is in the domain of L, we can write the generator of the process of u that's given by the complete set of equations. So you can quickly see that if you just forget about these two things, then this is just a generator for this Gaussian process. Just a generator. Then we add, because we have the noise jump noise of size less than 1, this corresponds to that integral, and jump noise size is greater than 1, that corresponds to the other integral for every u in the domain of A. So now we pose the martingale problem. LF is a generator as defined in 14, then the last equation we just saw. Then a given an initial measure P on H, a solution to LF martingale problem is a probability measure P going from this Borel space into 0 comma 1 on this probability space such that this P satisfies this, and this quantity, this process is a martingale where f is in the domain of L. F of z of t minus f of z of 0 minus integral 0 to t. LF is the generator what we defined just earlier. Then this quantity is a R valued locally square integrable P Laplace martingale. This is a martingale with respect to this filtration ft tilde. Then the basic problem of this martingale problem goes back to Stoke and Varadhan. They did they formulated the martingale problem for the diffusion processes, and also they got that the famous American Mathematical Society prize, Steele prize for this their contribution on this area. Seminal paper in 1969, 2 paper in communication in pure and applied maths. So that brought into the big field of this martingale problem for this formulation of the martingale problem for this stochastic processor. Of course, this martingale problem in general, we already know that we have seen several in lectures that what is the strong solutions for the stochastic equation. Then there is another formulation. Here you can see that I will come to that weak solution. The strong solution, the probability space is already given to you. The Brownian motion is given to you, and the coefficients of, if you just start with the equation, if you just dx of t equal to b of x of t into t dt plus sigma t comma x of t into t, I am just writing in the Gaussian case. Then if you just start with this equation, then if you are given a probability space omega fp is priori given. I am just talking about the strong solution. It's priori given and the coefficients B and sigma are already given to you, then the filtration generated by this Brownian motion is already given to you. Then we are trying to come up with a solution in terms of the integral equation. We need to find a progress, I don't know, I can put it as something like x cat. This is a solution for this equation such that this is x cat of 0 plus integral 0 to t. It satisfies B of x of s ds plus integral 0 to t sigma of s x of s dB of s. So then I need to find, I can put, so we need to find the stochastic process x stat which satisfies this integral relation, then we call such a solution is a strong solution. Suppose then this is not the case. Here in order to get such a strong solution, at least we need to assume that this minimum requirement that they pose is that Lifschitz continuity of these coefficients B and sigma. Suppose those coefficients, we don't have such a condition on those coefficients, then how to talk about the solutions of this problem? Then they go for the weak formulation. The weak formulation of the solution is this probability space is not priori given to you. Then you have to come up with this probability space under Brownian motion on which this under filtration associated with such that on which this relation is satisfied. Right? So you understand the problem is completely different. Priori this probability space is given, then we are trying to come up with a stochastic process such that this integral relation is satisfied, then such a solution is called the strong solution. If that's not the case, then you have to come up with an appropriate probability space under Brownian motion such that this integral relation is satisfied. Then this Stoke and Varadhan, they come up with another problem. In that case, for instance, this equation, why we need a weak solution immediately, this is the famous Tanaka's ODE, the stochastic differential equation, dx of t is equal to of x of t into dB of t. Then this function is not even, this is not Lifschitz continuous, then how to talk about the continuity of, solutions for that kind of differential equation. This is a signum function, SIGN is a signum function. Then in that case, but this problem doesn't have a strong solution, but it has a weak solution. Brownian motion is the solutions for that equation. So in that context, the martingale problem, Stoke and Varadhan posed in this way. So we are, again, in this case also we are going to come up with an appropriate probability space and the filtration such that this quantity is a martingale for any f in the domain of L. Martingale with respect to this ft tilde, P martingale is a P martingale because this is a probability measure we are going to come up with. But there is an equivalence relation between this martingale solution and this weak solution formulation. Whenever this system has a weak solution, that's equivalent to the martingale problem. If you have a martingale solution, then one can show that that is also a weak solution. There is an equivalent relation that's given by Yamada Watanabe. So we are going to see some of the things here. So now existence result is an open domain in RD. I didn't say anything about whether it is a bounded or unbounded. Then given initial probability measure B on H, which satisfies, this is finite, x square dpx is P is the initial probability measure. Then there exists a martingale. I didn't say any of the conditions here, all the conditions are there. I just wanted to make the theorem simplified in the presentation. So all the conditions, whatever I stated on the Gaussian noise coefficient and also that jump noise coefficients are there. So then in that case, then the given initial measure probability measure P, there exists a martingale solution to the system, what with the Navier-Stokes with Levy noise. So then the Metivier in 1988, he proved that the existence of martingale problem is equivalent to the weak solution of the stochastic differential equation. So then Yamada Watanabe, they came up with the existence of a weak solution together with the pathwise uniqueness property. We will see what is pathwise uniqueness. If we have a weak solution, then that solution is we have a pathwise uniqueness, then we have the uniqueness in law. That means we have a unique martingale solution or the unique measure, probability measure. So what is pathwise uniqueness? If U of t is the process, then U dash is the process, U prime is the process like this. For any two solutions defined on the same probability space, whenever this initial data coincides and the covariant matrix this coincides, this Vk coincides, then this process and also coincides, that's the pathwise uniqueness. So then the pathwise uniqueness, this is the pathwise uniqueness. If U and V are be the two paths and the same probability space with the same Q inner process and the Poisson random measure Vk satisfying the system, then there exists a positive constant satisfying this relation, inequality. One can quickly see that whenever these initial data are equal, then when dimension d equal to 2, we have to just concentrate on this finiteness of this integral. When d equal to 2, you can quickly see that this is just v square norm. This is a v norm which corresponds to the v norm what I started the space. Then this is finite from the energy estimate we are going to see in quickly. This is finite due to the energy estimate in the dimension d equal to 2. When we go for dimension d equal to 3, this corresponds to the term something like this goes v norm of power to the 4, where we don't know whether this is finite. So then for d equal to 3, the solution u is pathwise unique, provided this condition is satisfied.
Now u to the 4.
Right, this is the v norm. Right, H1 norm in principle is the H1 norm. So the quadratic variation and Mayer process. So MT is a locally square integrable martingale. Then there exists a quadratic variation and the Mayer process given by this quadratic variation and the Mayer process. It may look like a big expression, but the quadratic variation, this is like a compensator of the quadratic variation. You can see that this minus this is a martingale. This is whenever the process is continuous, these 4 terms won't appear. Then only we will have these 2 terms. Then the process is continuous. This quadratic variation and the Mayer process coincide. That is just coincide. In other cases, if we have that jump noise, then they won't coincide. This Vk is the Poisson random measure. This is the compensator we have just seen. Then this difference is a martingale. Vk minus this mu k, the measure P minus mu, gives the integral martingale. This integral is a martingale. Therefore, this difference is a martingale. So then we are going to project the system into the finite dimensional one by using the Galerkin approximation. Then with the orthonormal basis E1, E2, etc. in H which are included in V. Then Vn is the space spanned by these basis functions. Then this Un solves these finite dimensional Navier-Stokes equations with this MT again given by the finite dimensional martingale approximations given by these quantities. Then the corresponding measure Pn which is defined in dO0 to dV and in principle in Vn, but we have this embeddings. Then these approximate measures Pn are defined in this space d0 to Vn or in V dash such that this quantity is again a martingale where this Lf is a generator associated with this finite dimensional process. I have used the same notation, but this Lf is for the finite dimensional differential equation, Navier-Stokes equation we just wrote it before, is a Kachan valued locally square integrable Pn catalog martingale. So then, if G is in this, we are now going for the energy estimates. Whenever G is in the L20 TV dash and this initial measure satisfies this condition, this MT is defined in Kachan valued locally square integrable Pn local catalog martingale, then this energy estimate is true. So now again we are coming to this tightness of measures. This is what Professor Sundar was talking about. Whenever this measures Pn is a probability measure Pn on a completely regular topological space, it to converge to a measure P for any bounded continuous functions on omega tilde over path space, this limit holds true. So then in order to arrive at this situation, then we need to talk about the tightness of those measures. Then we need to produce a weakly compact set on which these measures are tight. So for that we are going for this Prokhorov-Varadarajan theorem along with actually Aldou's condition. I have not stated those conditions, Aldou's condition and also that theorem of Repelledo, that's for the semi-martingale formulation. So now we are defining, this is our path space, we know that this is the path space we started with, then we are coming up with the appropriate topology. This is Square topology for this space D0 to V dash, and these are the topologies associated with these spaces. Then this intersection, each space is completely regular and continuously embedded in this space L20 to V dash, and the supremum of these 4 topologies is tau. Then now we are going to work with the supremum topology tau. So then the sequence of probability measures, I have not given any proof here. This sequence of probability measures Pn defined on this space with support in this support you can gain from the energy estimate what we have proved over there is tight in this space T0 to V dash. So now our aim is to show that this probability measure Pn is the approximate probability measure we have it, and the limit measure satisfies this relation. That means this MT is a martingale with respect to this limit measure P. One can quickly, I don't know whether Professor Barbara spoke about the martingales. Initial. Oh, okay. Okay, so then everybody should know that what is martingale here, what I am talking about the martingale, right? So then, in order to show that we need the limit measure also satisfies this relation. That's what I have to show. Whenever we know that this is true, this Pn, this MT is a martingale with respect to this 5-dimensional measure Pn that's equal to 0 for every n, and also we have established the tightness of measures in this P. But we don't know whether this limit measure will satisfy this relation. Once this is achieved, then we are done. That means that this is this MT is a P martingale. So in order to achieve this, we are going to use what we have just seen about to pass those kind of limits. We have to show that this M is continuous. Otherwise, this doesn't hold true. Because for any bounded continuous functions, those kind of limit exist. Therefore, we have to show that this MT is continuous on this omega tilde. But we have seen that we have just established only in this space, the tightness of measures only in this space. That is not sufficient. This comes weak star topology, this comes weak topology. We don't have any strong topology to work with. Therefore, in order to establish this, then we are going to make use of the compact impedance V from H to V dash. This impedance is compact. Then we have the following compactness theorem. This is the following compactness theorem we are going to use. Then, so we have already established that this Pn, making use of those results, we can just show that this the tightness in L20TH with the strong topology T4 is the strong topology associated with this space. Then these the measures Pn are tight in the Lucent topology. We have already shown that the measures are tight in omega tilde. Then and also these measures are tight in the product. And this topology omega tilde intersection L20T is endowed with this supremum topology. Supremum topology is the supremum of 4 topologies we started with. So in order to prove that. Now we have done that these measures are tight in that omega tilde intersection L20T, we have 0TH, and that means that we have that convergence of those measures, strong convergence is also there. But in order to show the continuity of this martingale, MT and omega tilde, we are going to use the Minty stochastic lemma. So for the first general stochastic PDEs, we had derived it in 1976, and Metivier, he has written a book on this subject in 1988. And Sridharan, he used that Minty stochastic lemma for optimal control problem with Gaussian noise, stochastic optimal control problem with Gaussian noise. Then, so now we are going to talk about the local. In order to get into this result, we are going to use the local monotonicity of the operator theta of u plus lambda u, where theta is this AU plus BUB is the nonlinear operator. Therefore, theta in principle nonlinear. So for a given rho greater than 0, p greater than d, why this is local monotonicity, because we are going to work with only within this ball BR. We are going to use only when the case p equal to 4, but we have derived this general result. Then for any u in V and V in BR, then this W satisfies this result. So now we are going to, you know that this nonlinear operator which maps from L, we have also seen that in Professor Sridharan's lecture, this maps from this omega tilde whatever we have from L20 to V dash, doesn't go to that usual space which is available in that omega tilde. Therefore, we are in the situation of the product topology omega hat, omega tilde cross L20 V dash. Then, see again we are coming up with the canonical right continuous filtrations, ZT hat in the product topology. And this measure, this finite dimensional measure P hat n, this is the image measure which corresponds to Pn, which satisfies these two relations. That means this MT hat is a martingale with respect to this measure Pn, P hat n. So taking into that point into account, then we are going to show that the limit measure of this P hat n satisfies those relations. Then the limit measure of P hat n also satisfies those conditions. Then in order to show that, we are going to derive something called Minty stochastic lemma, making use of this local monotonicity argument. Then this limit measure, assume that these measures P hat and of course this measure converge weakly to a measure P hat on omega hat, such that the relation N2 whole, relation N2 is just this is a martingale, P hat and martingale. whenever that is true, then we are going to show that this limit measure phi hat satisfies this probability of this guy for any omega v in omega hat. This equivalence is always equal to 1. So for that we are going to come up with the test function zeta. I am just giving only 2 lines here to how this we are going to use that local monotonicity argument here. Then define this function xi is equal to this integral. You can see that rho of t is in terms of this test function over 4. Then the local monotonicity is restricted to we have proved it for p. When p equal to 4, then we will have the terms like this. Then we are defining the rho dot of t that brings the derivative of this time derivative of this guy. So and then if you just compare this one, whatever be the quantities inside with the previous one, local monotonicity theta of u minus theta of v, w is the difference u minus v. You can quickly see that this lambda is the constant which depends on these powers. When p equal to 4, rho is the bound of this v, then p equal to 4 exactly that rho power 4 what I have taken over there. So then this is positive by that argument, the local monotonicity argument. Then this integrating with respect to that omega hat in the p hat n measure, the finite dimensional measure, then this is positive. Then we try to show that this limit measure also satisfies this quantity, this inequality which is greater than or equal to 0. Limit measure of p hat n, that is the whatever I just wrote it here. Integral with respect to d phi hat is also greater than or equal to 0. Once we achieve this, then by using some this theta is a hemi-continuity, then using the hemi-continuity argument, then we can pass the limit and prove that the result what we stored over there. So finally we have shown that this is continuous. See in the product topology omega hat for any measurable function phi in this bounded measurable function in omega hat, bounded continuous function in omega hat, then the final thing what we need here is that the convergence arguments. Whatever we have stated here, everything is we have shown so far. Omega hat is loose in space, p hat n is a sequence of probability measures on omega hat, converging weakly to a measure p hat. Everything we have now shown as n going to infinity. And G is just I am taking notation, this is for the martingale empty hat. Then G is continuous in omega hat, that we have proved now. And we can also show that this is finite. Expectation with respect to this p hat and this empty hat 4 to the power 1 plus epsilon. This is also finite for some epsilon. For the Gaussian case, one can refer to Professor Sridharan paper or that book by Fursico and Vishik and Fursico. Then if this is true, then this limit takes place as n goes to infinity. So now we are in the situation, once we arrive at this situation, then we can pass the limit, everything we have shown, whatever we needed so far, then the limit is indeed exists. Then we know that this empty is a p n martingale, but therefore this is equivalent to 0. That means this is equivalent to 0. This implies that the empty is a p n. Yeah, this implies that this empty is a p martingale. So then I didn't say anything about when O of domain is unbounded. Here, so far, maybe this is a printing mistake, this should be unbounded. So far we have just seen that when the domain is bounded, when the domain is unbounded, then we can see that due to Ladies-Singh inequality, this norm is bounded by this quantity. This is true for when dimension 2 or 3 irrespective of the dimension. Then as I said, when d is equal to 2, you can see that this is just a L2 norm, this is the V norm, both the quantities are bounded due to energy estimates. But when d equal to 3, we don't know this space, this nonlinear operator belongs only to the L4 by 3 of 0 to d V dash. Therefore, we don't know how to apply the Minty-Stochastic lemma in dimension 3. So, but we can prove the continuity of this martingale empty only just in the continuity in this case. So in that case, we are going to come up with a test function fu. This is the test function given by p. This phi is C0 infinity functions in Rm, and the theta k is coming from domain of A. Then whenever this un converges to u in this omega tilde for the supremum topology, the losing topology omega tilde, then this martingale is continuous on omega tilde. So only continuity is needed, and that is missing due to the lack of this Minty-Stochastic lemma for 3D case. Then making use of this result, we can proceed the same thing for this 3D case also. So now, but if it, so then what is the exact problem here? Because we don't have that, when we assume that domain is unbounded, then in this case the compact impedance doesn't hold true. If we don't have a compact impedance, then we have whatever be the compactness theorem we have used so far to get the tightness of measure doesn't hold true over there. Then these measures only tight, this Pn is only tight in D0T H weak. So that means that we cannot prove that this martingale empty, the continuity of the martingale on omega tilde either in 2D case or 3D case. So then in this the simplest situation like when sigma is just additive noise, then this pk, the Gaussian jump noise coefficient is also something like pk, doesn't depend on the state yu, then and also for the large jumps, then the Minty stochastic lemma still hold because the nonlinearity coming from that the other part, big nonlinearity b, we have handled through this Minty stochastic lemma. But when we go for this multiplicative noise, we need a stronger assumptions on the Gaussian and jump noise coefficient, something like they are continuous in the weak topology of H. Such assumptions are seems to stronger than, but we are not going in the direction. But there are, I think there is a there are some papers in this direction also going into that weak topology of H, assuming that these noises are continuous in the weak topology of H. Then so then what we did is that cut the domain, this unbounded domain, into sequence of bounded domains OI and construct a martingale solutions in each of the bounded domains, and then pass the limit so that this limit measure P exists even in the unbounded. This is the argument we did in our paper. So I have just given few lines of pathwise uniqueness. When U and V are two paths defined in the same probability space, then the difference is W, then corresponding for the Gaussian noise and jump noise. Then this W satisfies this martingale, semi-martingale formulation given by this finite variation part and the martingale part. So then, because of this Leddy-Sinskier inequalities, one can quickly see that, as I said in the uniqueness part, again the same bound we have a problem with that bound. When d equal to dimension equal to 2, then this term is uniformly bounded due to the energy estimate. So therefore, we don't have any trouble here. But when we go for d equal to 3, we don't have bound for this, then that term will appear. That's the term, the condition we put it in the uniqueness of pathway solution. So then apply the eta formula for this product, e power rho of t into w of t, L2 num of w of t square, then we will end up this. Then using stopping time argument, we can localize the martingale, that taking expectation that martingale term, whatever we wrote on the, this is the martingale term, this is 0. Then estimating this one and this one, we will ended up in this inequality. Then using Chebyshev inequality and energy estimate, we can argue that this tau m goes to this stopping time goes to t. This is the minimum of t or minimum of t comma tau m, then tau m goes to capital T, Sm goes to infinity. Then using Ronald inequality, one can achieve the uniqueness of pathway solution. Along with that, as I already said, this martingale solution is equivalent to the weak solution, and the pathways uniqueness along with the weak solution implies the uniqueness in law, or that this martingale solution is unique. These are the references. This is the really good book for the Levy process, and this is the paper for this Gaussian noise martingale solutions for the Navier-Stokes equations in Gaussian noise. And this is the Metivier book I was keep pointing out. And in this book we can found that the Skorogot topology. This is a recent book on stochastic partial differential equations with the Levy noise. This is the paper I was finding out by Sridharan for the Minty stochastic lemma. This is the famous book of Stook and Varadan. Then Yamada Watanabe, this is the classical paper for uniqueness of solutions and the equivalence to strong solutions in that.
Any questions, comments?
What was the wisdom behind using the background?
Pardon?
Choosing the background of the slide as
Little bit dark. Does it looks dark? It's not clear. Yeah, right. I want. It's not clear. I don't know, because when I always used to see from just in the laptop, it's not clear. Okay.
dark,
Right, yeah.
slightly darker.
Thank you.
Okay, if there are no questions, we'll thank the speaker again. And all the
This makes some problem. That's why he has gone into some low resolution area. The things.
For 5.
Yes. Excellent presentation.
Question is there? Yes, taken the video. It is fine.
Okay, sir. So, this is published paper.
Presentation also we can put.
This is published paper.
Yeah, whatever.
Okay.
Yamada and the strong distance.
Because we have a strong uniqueness, we can get it from this result, right? Whatever the uniqueness theorem being proved.
79 for 5.
It's a bit more condensed, but it's okay for
The problem with this presentation is that go to row resolution area. I didn't